In the beginning, there was nothing. No matter, no space, no time. Yet from this vast emptiness, everything we know today emerged. This is the story of how atoms, the building blocks of everything, formed from seemingly nothing. 13.8 billion years ago, the universe was born in a cataclysmic event known as the Big Bang. It wasn't an explosion in space, but an expansion of space itself, starting from a single, incredibly hot and dense point. Imagine everything in the universe compressed into a tiny spot, then suddenly expanding outward. This marked the birth of our universe. In the first moments after the Big Bang, the universe was extremely hot and dense, with temperatures around 10 circumflex 32 Kelvin. At such high temperatures, the known laws of physics break down, and a unified force governed the universe. Within a fraction of a second after the Big Bang, the universe underwent a period of rapid expansion known as inflation. During inflation, the universe expanded exponentially, growing from the size of a subatomic particle to that of a grapefruit in a tiny fraction of a second. After inflation, the universe continued to expand and cool. As it cooled, different forces began to separate. First, gravity split off from the other fundamental forces. Then, the strong nuclear force, responsible for holding atomic nuclei together, separated from the electromagnetic and weak nuclear forces. As the universe cooled to around 10 circumflex 15 Kelvin, about 10 circumflex 12 seconds after the Big Bang, quarks and gluons began to form. Quarks are the fundamental building blocks of protons and neutrons, while gluons are the particles that glue quarks together through the strong nuclear force. In the first moments after the Big Bang, the universe was like a hot soup made of quarks and gluons. This state is known as the quark-gluon plasma. In this plasma, quarks and gluons moved freely, not bound together into larger particles. Quantum chromodynamics, or QCD, is the theory that describes the interactions between quarks and gluons. QCD is a fundamental part of the standard model of particle physics and explains how quarks are held together by gluons to form protons, neutrons, and other hadrons. As the universe continued to expand and cool, the temperature dropped below 10 circumflex 12 Kelvin, approximately 10 circumflex 6 seconds after the Big Bang. At this temperature, quarks began to combine to form hadrons, such as protons and neutrons, through a process called hadronization. Protons and neutrons are types of baryons, which are hadrons composed of 3 quarks. Protons consist of 2 up quarks and 1 down quark, while neutrons consist of 2 down quarks and 1 up quark. These particles formed within the first second after the Big Bang. Within the first few minutes after the Big Bang, the universe cooled enough for protons and neutrons to combine, forming the nuclei of the lightest elements. This period is known as Big Bang nucleosynthesis. During this time, the first nuclei of hydrogen, helium, and small amounts of lithium and beryllium were formed. Hydrogen, the simplest and most abundant element in the universe, formed when single protons captured electrons. Hydrogen atoms consist of 1 proton and 1 electron. Approximately 75% of the baryonic mass of the universe is hydrogen. Helium, the second most abundant element, formed through a series of nuclear reactions. 2 protons and 2 neutrons combined to form helium-4, the most stable isotope of helium. Approximately 24% of the baryonic mass of the universe is helium. Small amounts of lithium and beryllium also formed during Big Bang nucleosynthesis. However, the universe was still too hot for electrons to bind to these nuclei, so it remained a hot, ionized plasma. Neutrinos, nearly massless particles that interact very weakly with matter, played a crucial role in Big Bang nucleosynthesis. They carried away energy and influenced the rates of nuclear reactions, helping to shape the abundances of the light elements. Approximately 380,000 years after the Big Bang, the universe cooled to around 3,000 degrees Kelvin. This cooling allowed electrons to combine with nuclei, forming neutral atoms. This period is known as recombination. During recombination, free electrons combined with protons to form neutral hydrogen atoms. Hydrogen, with its single proton and electron, became the most abundant element in the universe. This process allowed light to travel freely through space for the first time. The decoupling of matter and radiation during recombination led to the release of the cosmic microwave background, CMB radiation. The CMB is a faint glow that fills the universe, providing a snapshot of the universe when it was just 380,000 years old. Helium nuclei also captured electrons during recombination, forming neutral helium atoms. Other light elements, such as lithium and beryllium, also formed neutral atoms, although in much smaller quantities. The formation of neutral atoms marked the end of the dark ages of the universe. During this period, the universe was filled with neutral hydrogen gas, which did not emit light, making it dark and opaque. Over hundreds of millions of years, gravity caused regions of slightly higher density in the primordial gas to collapse, forming the first stars and galaxies. These regions of higher density were seeded by tiny fluctuations in the density of the early universe, amplified by gravitational attraction. The first stars, known as population of 3 stars, were massive and short-lived. They formed from primordial gas, consisting almost entirely of hydrogen and helium. These stars were responsible for the first generation of nuclear fusion, producing heavier elements through stellar nucleosynthesis. In the cores of stars, hydrogen atoms fuse to form helium through a process called nuclear fusion. This fusion releases tremendous amounts of energy, powering the stars and creating heavier elements. In more massive stars, helium fuses to form carbon, oxygen, and other heavier elements. Massive stars end their lives in catastrophic explosions known as supernovae. These explosions are so energetic that they create and scatter elements heavier than iron throughout the universe. Supernovae play a crucial role in enriching the interstellar medium with heavy elements. As stars formed, they grouped together under the influence of gravity, creating galaxies. Galaxies are vast collections of stars, gas, and dark matter bound together by gravity. Our own galaxy, the Milky Way, formed in this way. In the cores of stars, nuclear fusion creates elements up to iron. Heavier elements, however, require even more energy to form. This energy is provided by the extreme conditions in supernovae and other violent astrophysical events. During a supernova, the intense heat and pressure enable the formation of elements heavier than iron. These include gold, silver, platinum, and uranium. The explosion also disperses these elements into space, where they can be incorporated into new stars and planets. Another source of heavy elements is the collision of neutron stars. When neutron stars merge, they produce gravitational waves and eject large amounts of neutron-rich matter. This process, known as our process nucleosynthesis, creates many of the heaviest elements in the periodic table. The heavy elements produced by supernovae and neutron star mergers mix with the interstellar gas. This enriched gas forms the raw material for the next generation of stars and planets, ensuring that each new generation is more metal-rich than the last. About 4.6 billion years ago, a cloud of gas and dust, enriched with heavy elements from previous generations of stars, began to collapse under its own gravity. This cloud, known as the solar nebula, eventually formed our solar system. At the center of the collapsing cloud, material accumulated to form the protosun. As the protosun grew in mass, its core became hot and dense enough to initiate nuclear fusion, igniting the birth of our sun. The remaining material in the solar nebula formed a protoplanetary disk around the sun. Within this disk, dust and gas clumped together to form planetesimals, the building blocks of planets. These planetesimals collided and merged to form the planets of our solar system. The planets formed in distinct regions of the solar nebula. Closer to the sun, where temperatures were higher, rocky planets like Earth, Mars, Venus, and Mercury formed. In the colder outer regions, gas giants like Jupiter and Saturn, and ice giants like Uranus and Neptune took shape. The presence of heavy elements was crucial for the formation of rocky planets. Elements like silicon, oxygen, magnesium, and iron combined to form the solid, rocky material that makes up the terrestrial planets. Earth formed about 4.5 billion years ago from the collisions and mergers of planetesimals. The early Earth was a molten, hostile environment with frequent volcanic eruptions and a surface bombarded by meteorites. About 4.5 billion years ago, a Mars-sized body collided with the early Earth, ejecting a large amount of debris into orbit. This debris coalesced to form the Moon. The formation of the Moon had a significant impact on Earth's development, stabilizing its axial tilt and influencing its climate. Over time, Earth's surface cooled and solidified, forming a solid crust. Volcanic activity released gases into the atmosphere, creating a primitive atmosphere composed of water vapor, carbon dioxide, nitrogen, and other gases. As Earth continued to cool, water vapor in the atmosphere condensed to form liquid water, creating Earth's oceans. The presence of liquid water was essential for the emergence of life. Life is thought to have originated in Earth's oceans about 3.8 billion years ago. The first life forms were simple, single-celled organisms. Through the process of evolution, these simple organisms diversified and became more complex over billions of years. Life on Earth is based on a variety of elements, most notably carbon, hydrogen, oxygen, and nitrogen. These elements combine to form the complex molecules that make up living organisms, such as proteins, nucleic acids, and lipids. About 2.5 billion years ago, cyanobacteria, a type of photosynthetic bacteria, began to produce oxygen as a byproduct of photosynthesis. This process gradually increased the oxygen content of Earth's atmosphere, allowing for the evolution of more complex, oxygen-dependent life forms. Approximately 540 million years ago, a period known as the Cambrian explosion saw a rapid diversification of life forms. During this time, many of the major groups of animals first appeared in the fossil record. Vertebrates, animals with backbones, first appeared during the Cambrian explosion. Over millions of years, vertebrates evolved into a wide variety of forms, including fish, amphibians, reptiles, birds, and mammals. Mammals, which first appeared about 200 million years ago, are characterized by their ability to regulate body temperature, produce milk, and have complex brain structures. The extinction of the dinosaurs 65 million years ago allowed mammals to diversify and become the dominant land animals. Humans belong to a group of mammals known as primates. The first hominins, our early human ancestors, appeared in Africa about 6 million years ago. Over millions of years, hominins evolved larger brains and more complex behaviors, leading to the emergence of Homo sapiens about 300,000 years ago. The discovery of the structure of atoms has been one of the greatest achievements in modern science. Atoms are composed of a nucleus containing protons and neutrons, surrounded by a cloud of electrons. The arrangement of these electrons determines the chemical properties of an element. The periodic table is a tabular arrangement of the chemical elements, organized by their atomic number, electron configuration, and recurring chemical properties. The periodic table is a powerful tool for understanding the behavior of elements and predicting their interactions. Quantum mechanics is the branch of physics that describes the behavior of particles at the atomic and subatomic levels. It explains phenomena that cannot be explained by classical physics, such as the dual wave particle nature of light and the probabilistic nature of particle interactions. Nuclear physics is the study of the atomic nucleus and its interactions. It has led to the development of nuclear energy, which harnesses the energy released from nuclear reactions, and nuclear medicine, which uses radioactive isotopes for diagnosis and treatment of diseases. Understanding atoms and their interactions has led to numerous technological advancements. Semiconductor technology, which relies on the behavior of electrons in materials, is the foundation of modern electronics. Advances in materials science have led to the development of new materials with unique properties, such as superconductors and nanomaterials. From the profound nothingness before the Big Bang to the formation of the complex universe we observe today, the story of atoms is a remarkable journey. Atoms, the fundamental building blocks of matter, emerged from the simplest particles through a series of extraordinary cosmic events. This journey has led to the rich diversity of elements that make up stars, planets, and life itself. The evolution from nothing to everything continues to inspire our quest to understand the universe and our place within it. Each discovery brings us closer to comprehending the vastness of the cosmos and the intricate dance of particles that gives rise to the wonders of existence. Thank you for joining us on this incredible journey. If you enjoyed this video, don't forget to like, share, and subscribe for more fascinating stories about our universe. See you next time.